All right. I missed this one. How can I miss this voice right here? All right, guys. So everyone read this problems and see how can you proceed with this. Come on. All right, give it a shot. So you have through traveling sinusoidal waves described by the wave function given. All right. So I think everyone should be able to read this one now because everyone knows how to, sort of extract all the information from the uh, waves equation. So everyone should be in very good shape now. All right, guys. So answer the question saying that what is the amplitude of the resultant waves? First question. Second, what is the frequency of the resultant wave? So this is like a sort of like a check your understanding what we just studied. All right, guys, give it a shot and see how it goes. You want some motivation here? No, no. All right, I'll give you like a 2-minute head start just to answer this one. Maybe just 1 minute, probably. Okay, just give it a shot. Good. So I think you can just actually refer back to the previous slide if you like. Just take a look at it and then just say, hey, it's just come from the summation of the two. So if that is the only two that you are going to use anyway, so look at this one. Everyone, when I say everyone can read this, because here we go, same amplitude, yeah, same k, the coefficients in front of x, that's k, same. Oh, this is supposed to be t, guys. Sorry, not tau. You probably confused, like what? Is there any extra? No, nothing extra here. Okay, so same omega. So the only thing that different is going to be this dude right here. That is our phi, which is the phase difference between these two waves. Okay, cool. So with this, these things are good. Then all you can do is just go back, and if you like, you can just take this, okay, and then use it. That we know the parameter that shows up in the front. Let me highlight it one more time right here. That would be your amplitude, which is 2a cosine phi over 2. You can just use it here. There you go. So this resultant wave amplitude is going to be 2a cosine phi over 2. And that's it, because now we know the phi is just 0.25 pi, which is pi over 4. There you go. So you can say it's 2a cosine pi over 8. Now you need a little bit of the calculator, but that should be fine. Just pi over 8 and you're done. Cool?
Okay.
Not bad, not bad. What about the frequency? We already discussed this. When you saw the frequency, we said whenever you have the same wavelength going and then you combine them, the frequency will not change because they're sharing the same frequency. Or, I mean, if you look back at this one, you can see that you already discussed this. The omega that we got from the summation stays the same. Yeah, the parameter in front of t is still the same parameter. So there's no change. So what you have here is you say, okay, omega is still that number right here, 12 pi. And you are done.
Okay.
Cool. All right. So just want to make sure that you guys understand like the simplicity of this thing. It's just the additions of two waves. And actually, if you have more than two waves, you can do like 3 waves, 5 waves. Doesn't matter. They're all just adding together to get the resultant waves. All right. But what we are showing over here is if it's a 2 sinusoidal waves adding together, you have like, a nice and neat mathematical description at the end. Okay, try again, guys. So I think you got the idea of how to do the combination of 2 sinusoidal waves. Let's do the part that we actually do the real experiment, something that you can observe and see how it goes. All right, so you have a pair of speakers placed 3 meters apart. All right, cool. And then you have speakers that run by the same oscillator. So this one just guarantee that the wave that coming out from these two speakers are exactly the same, no difference. Now a listener is originally at point O, okay, which is at the center, and it's located 8 meters from the center of the line connecting the two speakers. Very good. So that's your starting point. And then the listener then walks to point P. So he walks up a little bit, okay. All right, and perpendicular, okay, which is a perpendicular distance 0.35 meter from point O before reaching the first minimum in sound intensity. What is the frequency of the oscillator? All right. Oh, there's a, oh, okay, I didn't see that. All right, thank you. That's very good. You got it right. Thank you. All right. So this one is more realistic, right? Because this is something that you can actually do in real world, setting. Because if you have two speakers, you can just plug it into your smartphone, generate like a download like a frequency generator. You can generate like a fixed frequency sound, and then you can actually hearing the sound coming out of it. And then when you walk around changing your position, then there will be some position that the sound that reached you is kind of like louder than usual, a little louder. And then when you move things around a little bit in some place, it will be quieter, and it will be loud again, on and on. All right. So that's this scenario that this is a realistic setup over here. Okay. First thing that you probably understand right away is while you are standing at point O, you're going to hear a loud sound. Does that make sense? The reason is because you are standing exactly in the middle. So if I draw this line, the green, so you can see these two green lines are having the same length. So it means at position O, which is at the center, you are going to get a constructive interference. Does that make sense? All right, so that's it. So that's a very quick conclusion that point O, this is when, if I'm talking about the path difference, is 0, because sound coming from the first and the second speaker reaches O at exactly the same distance. I mean, after travel at exactly the same distance. And that will lead you to the phase difference of 0 as well. No phase difference at point O. But now when you move a little bit further away from it, now you can see that the R1 is getting shorter than the R2. So this means wave that traveling along the R1 will definitely going to be, there's some phase difference than R2. That's what we want to figure out. So what we want to know is how much difference. So we're just going to take the difference between the two, and it's going to be R1 minus R2 under the absolute sign. And because we know that R2 is always bigger than R1 for sure. So you can just, write it down as R2 minus R1. So the R1 and R2 can be calculated using Pythagorean theorem without a problem. Look at the upper triangle in yellow. Okay, so that one is fine, but John, I can figure out R1, and it's going to be square roots, the opposite over the adjacent, a square plus b square, right? We don't need trigonometry here. So 1.15 square plus 8 square under square root. Does that make sense? Okay, cool.
Okay.
Now, the R2 is going to be square root, and then you do the height over here, 1.85 square plus 8 square. That's R2. So you have no problem calculating R1 and R2 exactly. That is fine. Now, once you take the difference, it's time for you to calculate the phase difference. Does that make sense? You got the distance difference. You got the path difference already. That's a delta R. What you want to do is you want to convert this into the phase difference. So you have a better logic of how you are going to deal with this. Or if you want, you can also compare this delta R to the wavelength. Same thing. Okay, because we know the condition of this one is it's either fall into two categories. If it's multiple of lambda, that is a constructive interference. If it's 2n plus 1 over 2 lambda, that will be destructive interference. Does that make sense? So you have choices for you to analyze. That's up to you. You can figure out the phi by saying that it's 2 pi times the delta r divided by wavelength. And if this is the case, I mean, if you would like to compare the phase difference, you would say if it's multiple of pi, multiple of 2 pi, sorry. So if it's a multiple of 2 pi, then it's going to be constructive interference. Does that make sense to you? Okay. And if it's the odd multiple of pi, so let me write it out. Okay. Just to be clear. All right. I can write this whole thing out. Oh, okay. No need. So let me say, if it's 0, 2 pi, 4 pi, on and on. And if it's odd multiple of pi, that will be destructive interference. So you have two choices for you to analyze at the position of consideration. You are going to get constructive or destructive interference. Okay. So your choice. All right. So in our case, what we have is we definitely going to be able to calculate delta R for sure. So just take the delta R, and if you want to compare with the wavelength, that can be done. Or if you want to multiply by 2 pi over wavelength, you will get the phi. Up to you. Okay. So now let's come back here a little bit. What about the conditions of this one? Now, however, the condition of this problem, they say, when you walk from O to P, you experience the first minimum. So what is the clue? What is the clue? You're starting from point O. Point O is definitely going to hear loud sound because it's a constructive interference, right? But then when you walk away from it, the sound will just down in the level of sound will drop. It's quieter until you reach point P. At point P is your first minimum. So that means at point P will be the point where, what the conclusion? At P, delta R is, guys, first minimum. Yes?
Okay.
With me? All right, because now at point O, everything is pretty much exactly the same. So the path difference is 0. But now when you walk up, all right, the path difference will start to diverge from 0. It's not going to be the 0 anymore, until you reach the first minimum. That is the signature saying that now your path difference is hitting the first possible destructive interference. And that is when n equal to 0. Does that make sense? That's the lowest possible numbers that you're going to get to the first minimum. So you plug in the 0 in there, and then you get lambda over 2. There you go. Got that one? All right. So that's it. So what you're saying over here is you take this R2 minus R1 and then multiply by 2. You will be able to figure out the lambda equal to what? Once you get the lambda, the wavelength of this one, then the frequency is just the speed of sound divided by lambda. And then most of the time, we will use this to be 340 meter per second, just like what we did in Doppler effect, on and on. Cool? All right, and you're done. That's it.
Okay.
But anyway, just to extend these problems a little bit further, think about this. If you keep walking, all right, just keep walking, and then eventually you're going to reach another point. Let me call this like point Q. It's going to come back and loud again. Does that make sense? So at this point, Q, your delta R will reach one perfect wavelength again. Not again, I mean, first time, but I mean, it's you're going to get the constructive interference back again. However, the condition is changed. It's not going to be like point O where there's no path difference. This is difference of one perfect wavelength. So that's why everything just get back to the constructive interference, everything in sync again, up and down. So everything is vibrating in phase. Okay, does that make sense? And if you keep walking, you're walking up. So you will reach another point right there. I can call it point M. At this point, the sound will quiet again. And at this point is where your delta R will reach what? Now 3 lambda over 2. Does that make sense? Okay, the original point O as loud, you're walking up first minimum at point P. And if you keep walking up, it will come back and loud again. That's when delta R is 1 lambda. You keep walking up to point M, it will quiet again. That's delta R is 3 lambda and a half. And if you keep walking up, now you can guess at point N, is delta R is going to be 2 lambda, on and on and on. All right. So if you map this one out, then you will have a spot, I mean, those spots where you have constructive interference, and there will be spots where you have destructive interference. Cool. All right. So that's sort of summarize what we have been doing until now. So at point P and M, the listener will hear nothing. Correct. Yes, exactly right.
Okay.
Very good. It's perfect cancellation. Yes. Cool. Alrighty, guys. So that's pretty good. Now we are at the last stop for this sounds business over here. Okay. So because we learned how to add wave, oh, actually I have a bigger one here. Forgot. I mean, it should be, it's going to be nicer to draw on here. Okay. Anyway. All right. It looks exactly the same after the zooming in. Okay. All right. So what we have over here is now the last stop is going to be super cool. So you already saw what happens when you have two waves traveling in the same direction. Now, what will happen if you have two waves traveling in the opposite direction? Do you want to try? Okay. So if you can try this one, then we're going to call it done. Okay. Because the conclusion that we have over here is going to be simple, but the derivation of this is going to be a little bit sort of like, you know, a little bit taking a little bit of time and stuff. So anyway, I will show you this. Okay, this is particularly about sound. Sounds kind of like work really well. But to be able to understand this one, it seems like it's probably nice to have sort of like a flashback a little bit. So what I'm going to do is this. I'm going to add a page. And let's talk about the simple waves on a string. Why not? All right. So let me draw this one for you. So I have all right. So you have string attached onto maybe two walls. Or you can think of this like a musical instrument, like guitars or anything like string instrument. You have like a very like a strings that attach between two ends, and it has some tension in it. Does that make sense? Okay. So this is like a string. And then once you plug your fingers on it, generate a wave, the wave will travel back and forth. The thing is this. So if you keep generating a wave and the wave starts traveling in here, it will hit the wall. So, I mean, let me give you an like a simple scenario. If you have only like a single pulse, the pulse will just travel until it reaches the other side of the wall, and then it's going to reflect back. But the thing is this, when you get this wall fixed in position, the reflections of the wave will flip upside down. That's what it is because of the reaction. I mean, the string try to pull the wall up, but the wall will exert the reaction to that and try to pull the string back down. All right. So that's why on the way out, or you can say that the reflection of the waves, on the way that wave has to travel backwards, it will get that reaction, pull everything down, and it's going to go down in the bottom out. You go top in, the bottom out. That's what it is. So it just go like this. But now you imagine that if this wave is a continuous wave, so that means every time that you send in the continuous sinusoidal waves, the one that we're familiar with, the one that coming out will be opposite to that. Does that make sense? Okay. So if you just only focus in the region in the middle, so it means just in between the two, it's going to be exactly the same scenario when you have like two waves, but it's traveling in the opposite direction, like that, and try to pretty much, merge or whatever, superimpose, and then get to the resultant waves. Okay. But the only thing that is different between just this figure and the one that you saw earlier over here. Here. This one, the one that we started out with, has no conditions on the fixed end. We didn't put this wave between two walls or between two fixed ends. So this is just like a free floating waves traveling, one on the left, one to the right, and they just meet halfway and then they just depart and never come back again. But this one is different. This one, you have two walls waiting to bounce back the wave all the time. So it means the wave will just keep bouncing back and forth, back and forth, back and forth, back and forth, crazy, right? So there will be like a crazy superposition over superpositions over superposition. This is the kind of stuff that eventually will get you somewhere. When I say get you somewhere, what does it mean? It means here, the key point is this: the left ends of this and the right end of this stay fixed at all times. So when you have two waves trying to travel in the opposite direction, and then you say, Dan, it's a simple combination, right? Just add them. But the thing is, by adding this, you cannot take any summations into your final solution because you can only pick the summation that showcase that, hey, this position on the left, I can call this like point A, and this point B must always be zero, guys.
Okay.
Isn't that weird? I hope it's not that weird. But the thing is, the reason I say is that weird because, you cannot just, the concept is simple. It's just summing two waves together, but you only have to pick the one that actually showing two ends, no displacements. Let's do it and see how it goes. All right. This one just for fun. All right. I'm not going to ask this in the exam or anything at all, but the conclusion will be simple. But let's sort of play this thing around with me a little bit. So let me say y1, the red, the one is the wave traveling to your right. So I'll give the amplitude. So everyone should be sort of comfortable with this writing now. I'll give it some wavelength k, 2 pi over lambda. And because this red wave is traveling to your right, I pick the negative sign, some frequency, and then I'm done. Cool? So this is just a constant speed wave traveling in the positive x direction. I'm doing the same thing with the green. Same amplitude because it came from the reflection. It's still sinusoidal anyway because we can imagine that the green is, driving to the left-hand side. So the only thing that is going to look different is just one is negative sign between, one is positive sign between. Does that make sense, guys? So far so good. Now I have two waves traveling in the opposite direction, but they are look alike. Same wavelength, same frequency, same amplitude. Guys, find me the resultant wave. Come on. Woo.
No.
All right, so we're gonna have the same fun as we had before. Using the same identity that we saw before is I can pull out the common factor A. Side A plus side B is 2 sine A and side B, right? So I have a factor 2 over here, okay? And then I can side off the sum over 2. So let me do that. For clarity, I'm just gonna write down everything. The sum over 2. There you go. And then followed by the cosine and followed by the difference over 2. I should put this at a bracket. It looks nicer. Okay. So the difference over 2. Here we go. Already. Cool. That's nice looking. Okay, just make it cleaner. There you go. All right. So you guys with me? I'm using the same identity again. Okay. Now the nice thing about this one is some can get canceled. Here we go. Omega t just gone in here. Kx gone in here. So what I have is just going to be 2a sine. Now I have 2kx divided by 2. So I have kx here for the sine. What about the cosine? I have minus omega t. So I have 2 minus omega t and then divided by 2. So 2 cancel. And cosine are positive or negative are exactly the same. So I just write down omega t. And that is done.
Okay.
What do you see? Guys, what do you see here? This is going to be a weird one because, well, Ajahn, all right, I got it. I just apply superposition principle. Whenever I see y1 and y2, I just add them, utilize a little bit of trigonometry identity. That's fine. But what you get at the end is that's a weird looking wave because you don't see kx minus omega t anymore. They got split out. Kx is with the sine, omega t is with the cosine. But it's still a wave or not? But it has to be a wave because it came from the combination of these two waves. So it's still a wave. But there is a specialties of this one, guys. Here we go. How can I associate the fixed condition that I just imposed there? Well, Ajahn, I want the left ends of this to be 0. I want the right end of this to be 0. So let's say if I sort of put an axis to it, and let me call this x axis, and that is your 0. And let's say the length of this one is L. So what I want is at x equal to 0, the wave always 0. Does that make sense? No matter when. Always 0 no matter when. So look at this. The time keep flowing. Time never stop. 1, 2, 3, 4, 5, 6, 7, 8 seconds. So the only way that I can keep this point A to be 0 at all time, the condition that I have to do is just I have to say about, okay, I'm going to have to take this whole thing here, set it to 0. Does that make sense? It might not be the whole thing there, but at least the one that I can make it 0 is this dude right here. That's the only thing left for me. Okay. So that's what I want. But from the look of it, Bajahn, when you substitute x equal to 0, it's fine. Sine 0 is 0. So this is good. So this one is gone. Try another condition there. At b, x equal to L, y must also be 0. Whoa. Now, let's have some play to it because that means sine KL must always be 0. You guys with me now? The condition at x equal to 0 seems to be always 0. So you're safe there. However, you need to pick the condition at the L to be 0 as well. And at that point, you say sine KL must be equal to 0. How can you make this sine KL to be 0 at all times? Well, John, that means your argument right here, KL must be multiple of pi. You guys with me now? Sine to be 0, your argument must be either 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So that means, oh, Ajahn, so that means I can actually taking just only some wavelength of this. Here we go. K is 2 pi over lambda. So I can say 2 pi over lambda L must be n pi. Yeah. Okay, almost done, almost done. Stick with me here. Pi cancel. So that means your lambda is going to be 2L over n. Whoa.
Okay.
What does this mean? It means n can be either 1, 2, 3, on and on, right? Because according to this condition right here, n is either 1, 2, 3, on and on. So this is the final result. It turns out if and only if you're going to have the wave traveling here inside this one, you have to meet this condition. The condition where the wavelength gonna have to have some particular value only, guys. Isn't that cool? I don't know you call it cool or not.
No.
But the thing is, there are not like, you cannot put any wavelength into this. The wavelength that will show up in here has to match the condition of at point A and point B, no movement. So you say, okay, to be able to adhere to that rule, so what I want to do is just make sure that the lambda meets this condition right here is 2L over N. Okay, when this condition is met, then what you have over here is you have the wave inside this system according to the conditions. And what are these? So look at this. When I substitute n equal to 1 to it, okay, follow me here a little bit, guys. So when n equal to 1, lambda equal to 2L. When n equal to 2, lambda is L. When n equal to 3, lambda is 2L over 3, on and on and on, right? So what I'm saying over here is it means there are only some wavelength possible that you can fit into this system right here. And the first one is when lambda is equal to 2 times the length of this string. So that means the wave that you can fit into this is going to look like this. Here, guys, here we go. All right, I'm going to draw this one big. Yeah. Right there. You guys with me? Because the lambda is 2L. So 2L must be twice as long over here. But I only fix everything within just the length L. So I take the one out. That is my conditions that the wave can be fit in here. If you don't like this one, n equal to 2, require that the lambda is L. Does that make sense? That's also possible to fit in here. Okay, what the wavelength doesn't meet the condition, what if, right? It means it won't happen. I mean, it won't show up at all in here. It will just dissipate out, gone, bye-bye. Because we want the condition here, which came from here, which came from there and there. Does that make sense? The only way that you guys can have a wave traveling in here, those two ends must be fixed. So by having those fixed ends, pick only some possible value of lambda. So if it meets the condition, then the wave will keep us correct. Exactly right.
Okay.
Okay. So that means it's either that first one, the second one, or say I can keep moving to L over 3. So that means it's just like gonna be this. Bam. See, every time that I draw this curve, which is the wave, I have to start from 0 and I have to end at 0 because that is our constraints. That is our restriction. I cannot get away from it. It's sort of like it's controlling me. It's like you need to start from 0 and you have to end at 0. And that is standing wave, guys. Whoa.
Okay.
The reason it says standing wave because there are some points in this wave that does not move at all, which is in this case is obvious. It's left end and both ends, left and right ends of this string. However, the conclusion is simple. The reason I try to show you how it's done here because I just want to first showing that the superposition principle works. Second, I mean, you need a little bit of trigonometric identity to help sort of like clean things up a little bit. Third, this one is a special case. You have some restriction on the conditions of the movement of the medium. Left end has to be 0 displacement at all the time. Right end has to have 0 displacement at all time. So because you have this restriction or conditions, then not all possible waves can be fit in here. So that's why you get only some possible wavelength that can show up in here. And once you have that, we have a name for it because there are some parts of this wave that doesn't travel at all. So we call this standing wave.
Okay.
That's a recap of everything. However, when we understand the concept of, okay, you have to make waves that adhere to the rule or the constraints. Come back to our slide, guys. Do you start to feel something here now? So first, I hope you understand that there is a standing wave keywords here. But now we're going to apply that concept to sound. All right. Sound is not a string. The string is the transverse wave. You can fix both ends. But for the sound, you need air to travel. So the first type of stuff that possible is in a tube. And now you start, oh, all right. And yeah, whenever you have a tube, then you can create sound, right? You have instruments, you have flute, you have everything, and organ, pipe, and all this stuff. Then those are possible to generate sound. And that's what it is. The reason that you get a fixed frequency from one length of tube, because you only be able to pick particular wavelength to fit in that tube. You understand it now?
Okay.
Does that make sense? That's why if you have a tube, yeah, and then you blow that tube, yeah, I should have that straw somewhere. Okay, but anyway, I'll do that later. So the thing is, that tube will only generate a single sound because that is the only frequency that works in there, or maybe only some frequency that will work in there. All right. So the only thing that you need, you don't have to go through this trouble anymore. Look at this, John. If you have like open tube like this, the air can oscillate back and forth freely on open ends, right? It can bounce, whatever. So that means you should have like a maximum amplitude on the left and on the right. That will be the best case scenario that you're going to get. So we're going to call the position where the medium can oscillate the most antinode. Okay. And there will be position that the waves doesn't move at all. You're going to call it a node. So back in our example over here, what you saw over here is this is the node. This is a node. The left ends of the string is a node. The right end of the string is the node. And in the middle, where in the first case, if you look at the first case here, in the middle there, that is the position of the antinode. Does that make sense? Okay. All right. So if you look at the second case, the one that you have one twist over here, then you're going to have two antinodes there. And then you're going to have three nodes in between. And I don't know, it looks really bad now. All right. But I can draw better here. Okay. Sorry. I will just keep writing on top of each other all the time. Okay. All right. Give me a minute here. There. All right. So there you go. So you have, this is the first possible. So node is on the left, node is on the right, and antinode is in between. Cool. And then if you say, oh, Adan, I can fit like this as well. It's a node on the left always, node on the right always, but then you can have extra node in between, and then now you have two antinodes. Something like that. Cool. All right. So now we're going to use the same logic over here, because now in the tube, okay, let me use red color. Oh, okay. I'm going to use red color here. So what you have over here for the tube, because we allow air to travel very hugely, whatever, at the end. So we should be able to put two antinodes on the both ends of the tube. And you just try to fit the waves, the sound waves in there. Does that make sense? It looks really bad, I know, but I don't know how to explain this like without going too much thing. Okay, here we go. You just want to go from big to big. The easiest way that you can do is you haven't had any twist just yet. That's what you do. But at least you go from antinode to antinode, the highest oscillation to the highest oscillation next to it. All right, it might be clearer if I do this. All right, another possibility about John. Let's do a little bit, one more twist there. I'm gonna go like this. Does that make sense? That's from big oscillation to another big oscillation, which is, okay, one wavelength away. And then I can do one more if I like. I start from antinode, that's the key. I can get one more twist. Oops, that's bad. One more twist there. There. That worked too. Still pretty bad, but I hope, okay, there you go. All right. So this is what it is. I try to sort of like do the analogy with the string over here, right? Because you have a fixed condition that both two ends must be a node. So now I can do 3 twists over here. There you go. Oh, off. There you go. So now I get extra nodes here, extra node there, 3 anti-node in between, on and on. So now your game is now easy to play. Just make sure that you know what is going to be your fixed condition at both ends. And the rest, you just draw any waves that fit those ends condition, and then you're good to go. All of these are all possible waves that you can fit in our system. Okay. However, the reason I try to write just only this because just want to make sure that the actual wave gonna look like this. I mean, when I say actual wave, mean if it's a string, it's gonna look like this. But if you look carefully here, see, I don't know why the textbook love to put it in. I know why. I mean, but the textbook try to put it in a loop type. When I say a loop type, because don't forget, waves never stop. It keep traveling, keep traveling, keep traveling. So it means that we just have some oscillation going on all the time. So that means in reality, wave will just going fluctuating back and forth, back and forth, back and forth. So that's why they can usually put something like this to it. There you go. There you go. Because in reality, this is what you're going to observe as well. If you have a guitar string and then you plug on it, it will vibrate up and down until you see like a loop coming out of it. Okay, I will have a simulation for you guys to see next time. But today we just try to understand the theory first. So that's what it is. So I hope, I mean, the key point that is sometimes I think is hard to understand is you have to take into account that there are only some possibility of waves that can be fit into this type of system. And actually this one is called boundary conditions. And for those of you that maybe took calculus 3 courses already, this is part of the differential equation toward the end. You have like boundary condition problems on and on. This is part of it. This is one of it. Why do we want ends to be antinode? Okay, that's a very good question, but we not, well, when I say we want, mean because that is the condition that eventually will give you the most sustaining waves in this system. When I say sustaining, it's what it is. Just like your previous question, in the string can actually generate crazy amount of wave, right? It just go back and forth, back and forth. But the only one that eventually gonna last is the one that fits the condition at the end. Does that make sense? So this one is the same thing here. Actually, you don't really want in the first place. You didn't want it. You didn't want antinode at both ends. But when you let this wave going crazy in there, the only thing that's left in here is the one that look like this. This is the one that's gonna last the longest and is most sort of like sustainable configuration of this system. Okay, so I know this topic is, I mean, I want to teach this one because it's so hard to understand from the fundamental understanding of this one, but it's so easy to calculate. This is like annoying part of this problem. Is, well, it's not, it's a good annoying in the sense that you can just look at this figure and then calculate the wavelength by just counting. You can say counting the loop, you can counting the wave, you can look at the shape of the wave and calculate the wavelength. So it's so easy to do, but the underlying thing is so hard to understand. All right, and this is what I'm going to show you next. And I am going to, I don't know, this is like a homework or not, but I think it's going to be something that's kind of useful. All right, so if you do the search online and then you do the standing wave, okay, standing wave simulation, okay, and I think it's all physics. Okay, let me try first. All right, if I got that one right, and then I'll share this to you. Okay, all right, very good. There you go. All right, let me send you the link here. There you go. All right, in the Zoom. Guys, try this. All right, and this is gonna be your, well, it's not a homework, but it's something for you to play between today's lecture and next time. So I hope you get a better understanding of this one. And then I will show you how to deal with this problem very easily. I mean, solving this problem is simple, but understanding this one is another story. All right. Oh, it's I do it on my computer. Okay, let me show you what I mean by I can pop up the here as well. Alrighty. So what you have here with all physics here. There you go. And this is a good website as well if you want. There are so many interactive physics stuff that you can check out. And what I'm doing over here is the wave. And my here we go. All right, air column resonance. This is the one that I sent you the link. Here we go. All right, guys. So try this one at home and see how it goes. You just run it. And this is actual stuff that is going on. See, and then you can pick and choose air column close at one end and open at the other. And for what we are talking over here is we want to do both open. So you just pick that checkbox here, the second one here. All right, there is a question if the ends are not antinode, then the oscillate. Correct. Yeah. Okay, look at this. So over here, that the thing that I want you to play is this. If I try to use the or show just the original wave, this is the original wave that run from left to right. Okay. All right. Now let me show the first reflection. So every time that the wave changing the medium, which is from inside the tube and outside the tube, there will be some reflection going on. So this is exactly what we study, right? This is two waves moving in the opposite direction. But you look at the resulting wave. See that? You're almost getting nothing. Nothing. See? So let me adjust the wavelength. Let me change the wavelength a bit. There will be some particular wavelength. See? You see the upper one, those are the original two going against each other. But the bottom one, that's the resultant wave, the sum of the two originals. See, this has a higher resultant wave. So this one is the one that is going to tend to last longer. And it's going to give you a louder sound. So that's why the sound coming out from the pipe instrument like this, it's going to give you this wavelength. And if you can play around with this wavelength and on, and then you'll see that once you adjust away from this, run again, see? So now the sum of the two will not as high in amplitude as the previous one. So that means your wavelength doesn't work so well. But the complication of this one is this, guys. The reflection must happen on and on and on. So the nice thing about this particular simulation is this. The misunderstanding about this one is you just assume that there are two waves, right, meeting each other. But in reality, it's not. You must have the reflection on top of the reflection. And then you're going to have reflection on top of the reflection on top of the reflection. So you have super multiple reflection on and on. So you add more to this. So you have the second reflection, third reflection to it. And this one can go up to the fifth reflection, the reflection of the reflection of the reflection. So that's what I'm saying is after this combination of this, the only thing that is going to last and is going to be a sustainable resultant of this whole thing is going to be just that particular wavelength right there. Let me pick the good one there. I don't know which one is good. Here, so somewhere. All right. Next time we'll do mathematics, so we know exactly what's supposed to be 2.5. Kind of cheat a little bit here. All right, here we go. So I'm pretty close. I'm just going to run again. See that? Oh, it's kind of like, oh, whoa. Okay, here we go. It's kind of like freeze on me a little bit here. All right, but that's what it is. So you guys can play around with this and try to sort of like understand what this is. But that's what I said. The condition that we want is the one that we want to fit the antinode in both ends. There are so many ways that you can add on top of this. You can pick many wavelengths possible as long as two ends are antinode. And these are the two that is going to last last forever, let's say. Just keep riding back and forth, and then you get everything out here. Okay, does that make sense? I mean, at least a little bit today. It might not make sense, like perfect sense. Okay, what if you close one? Okay, very good question. You can play around with this as well. Try close it. Bam. Do I have to pause first? There. So now one end is closed. By not changing any wavelength at all, the condition that works before with the open ends will not work here anymore. See that? So the sum of the waves looks pretty bad. And I can show all the sum, or maybe the reason is low because it's sort of like displays so many things going on. Yeah, what you have over here is, so the resultant wave underneath is not as high as the open end anymore. So that means the wavelength condition that works for both ends open does not work with one open, one closed. And that's what we're going to solve the problems next time when we see. But at least play around with this simulation. It will help you understanding a lot, I hope. Cool, guys. All right, guys. So let's stop here. I think I talk a lot today, not a lot of calculations, but I hope that will give you a good background on what we need later. All right, guys. Take care, and then I'll see you guys on Saturday. Sorry for forgetting to record in the first half. All right, I will patch with the other section. Yeah. Okay, guys. Thank you. I'll see you. Any questions? Forgot to ask. All right. So if not, all right. See you guys on Saturday. Thank you. Bye bye.